Welcome everyone. So I'll be talking about disjoint set data structures. So is anyone unfamiliar with this? Okay, great. So I'll explain what it is. So it is a way to store a collection of disjoint sets represented as trees. So each tree, in each tree you have a bunch of vertices, and each vertex has a pointer to its parent, and you can follow the parents all the way up to the root node whose parent is itself. So in this setup, we have 5 disjoint sets, each with one element, and you'll apply, you'll successively apply the 2 operations of union and find. So this is the initial configuration. Then we union A and B. So now A and B become one set with B pointing to A. Union A to C, so C joins that set as well. And now we do a find. So we try to find from C, and we walk up all the way to the root. So the root is A. So the result of find C will be A. And then we continue doing some operations, which hopefully you understand by now. Okay, so this is a non-trivial union because I'm unioning these 2 elements here, but before I union, I need to actually find the the corresponding roots, and then I find I have to attach one of the roots to the other root as a child. So this imagine you're actually drawing a link from A to D here to form this new picture. Yeah, and then so now if you find C, instead of stopping at A because we union earlier, you'll stop at D. And okay, so this data structure is used, for example, in Kruskal's algorithms for finding minimal spanning trees. So I won't elaborate too much on it, but the important thing we are trying to ask is, what is the cost of these operations, right? So the cost of a find operation is basically how many edges we need to traverse from that initial node to all the way to the root. So it's the length of the path. And for a union, because we need to traverse 2 times, one for one node and one for the other node. So it's the length of 2 find paths and O1 for attaching one root to the other. So what I described just now is a vanilla unoptimized version, but there are some easy optimizations you can make to improve the performance immediately. So the first is path compression. So every time you perform a find query, you can actually sort of collapse everything along the find path down into the immediate children of the parent. So F's parent become A, E's parent become A, and so on. So clearly this makes future finds a lot shorter. And the second optimization is called weighted union, where because initially with union, right, there's a choice of which root to attach to which other root. But with weighted union, we establish a rule where the smaller tree gets attached to the bigger tree, as in this case, which actually makes the tree flatter in general instead of like this. This will be very important for the proof later on.
What operation is going from that one?
This is taking the union of these 2 sets. Yeah, so for example, union G of H, you will find A and you'll find G. I mean, assume these are different, so you'll find A and G, and it will attach G to A. It will update the link. So this is the big result which I will try to explain. So if you have a sequence of n-1 unions and m finds, the total time complexity will be given this function m times some inverse Ackermann function. So if you divide it by the total number of operations, you can see that the average time taken by an operation is given by the inverse Ackermann function, which is not a constant, but it grows very slowly. So, and there's a very important note here where union here actually just refers to the act of attaching one root to the other. So when I described union earlier, I was actually doing 2 finds under the hood. So if we adopt this new definition of union, it's reasonable to assume that there will be more finds than unions, because for every union we do, we are doing 2 finds. So there's guaranteed to be more finds than unions. So before explaining what the inverse Ackermann function is, I have to explain what the Ackermann function is. So I think the easiest way to understand this is via hyperoperations. So we can actually define a sequence of operations where each operation is defined as applying the previous operation n times. So for example, you have addition, applying addition n times gives you multiplication, applying multiplication n times gives you exponentiation, and so on. So you can represent this succinctly using Knuth's up arrow notation. And yeah, this grows very quickly. And also a note that this is the definition used in the paper, but this is actually not the actual Ackermann function, which is defined like this. But the general idea is still the same. So it also satisfies this recursion. Yeah, so just to illustrate the first few values of the Ackermann, so you can see the explosive growth, and by the time it reaches the 6th row or so, like even the first entry is already like so unpractically huge. So now we can talk about what the inverse Ackermann function is. So this is taken straight from the paper. It might look a bit weird, but that's because it's defined specifically for that proof to work. But for all practical purpose, alpha of m and n is less than or equals to, it's supposed to be 3. Sorry, I forgot to change that. So recall what we wanted to show in the previous slide. Okay, so you're ready to get to the proof. So I'll be following this paper by Tarjan, written in 1975. So the first step in the proof is actually to change our point of view, because in our original setup, we could have unions and finds intermixed with each other. So like union, find. And basically this makes the analysis very difficult, because every time we perform a union, we are changing the state because we are merging two sets. And every time we perform a find with path compression, we are also changing the state. So there's a lot of state to keep track of. But suppose we actually lumped all the unions together at the start. So if we lump all the unions, we actually first get a forest, connected forest with n nodes. And I'll just assume that the forest is actually a tree, because that's what the paper assumed. So if originally we had n minus 1 unions and m finds, now we can actually convert it into a sequence of n minus 1 unions at the start, followed by m partial finds on this forest or tree. So I'll just sort of run through the previous example to illustrate how it looks like. So this was our initial setup, and this is the T after we merged, we perform all the unions. So find A. So notice that for find A, we don't actually stop at D, because at this point, A hasn't been merged to D. So that's why it's called a partial find, because we don't actually go all the way up to the root. We just go up to some, we just traverse some paths and possibly stop halfway. So find A, find B, similar. Union of A, B. So find A, find C, union of A, C. So now because C and A are merged, so now this partial find of C will actually stop at A instead of C just now. And then, yeah, this is just running through the rest of the operation. So yeah, this doesn't follow weighted union, but the proof technique actually still applies regardless of weighted union. Yep. Yeah, so this is also when you apply a partial find, it can also change T. So there's also some state. So instead of CAD, it becomes CD. So I represent that by T prime. Okay, so some very important definitions you have to make for the proof. So for each element V or X, let's define its rank to be the height inside the initial T, because we call that T can change as we do partial finds. And if T is the tree at some point and we do a partial find on it, let the resultant tree be T prime. So there's some easy results which are pretty obvious. So for example, if V to W is an edge, at any point in time, the rank of W must be greater than the rank of V. And if you have a sequence of edges constituting a partial find, and so V is the start point and W prime is the end point, then we have that the rank difference actually, because W is initially V's parent, but after the partial find, now the new parent is W prime, right? So the difference in rank actually forms a non-decreasing sequence. Yeah, so for example, the sequence of green edges constitute the first partial find. So after V is initially pointing to W, but after the green one, V now points to W1. So now we perform the second partial find from V to W1, then to W2. So V now points to W2, and then the third partial find, it will go all the way up to V3 and so on. So this is just to give you an idea of how these partial finds operate on this tree we just constructed. Yeah, so this is another way of visualizing. So this is a sequence of partial finds with respect to the, at the top is a sequence of partial finds visualized with respect to the original tree. So after we do a partial find, we don't change it. But now what changes is that it's possible for edges along the partial find to actually skip, because technically C is now E's parent, but we're just retaining this original configuration. And this is just to illustrate the point that along an edge, the rank can actually increase by more than 1 now. So here it increases by 2, here it increases by 3. So now, okay, so after we made this transformation of the problem, now we have to bound the number of edges along the partial finds, because that's where the main cost of this union and find operation comes from. And then, yeah, so a trivial bound. So we can actually group all the partial edges by their sources. So all the partial edges from V, all the edges from V1, and so on. So you can see that such an edge must appear only once per partial find. So you can actually bound it by NM. So this is the cost from the partial finds. And if you add the cost of the unions, which is plus N, then you get O of NM, which NM plus N, which is O of NM, since N is less than or equals to M.
Sorry, for the previous slide, the original T, is it after all the unions already?
Yes, so we do all the unions at first, and then we get this thing. And then we sort of visualize how all the partial finds are performed with respect to this original.
Then the current T is when you are...
Yeah, if we actually update the parent, like if after the partial find, I actually update E's parent to be C, so like this.
Oh, I see.
Yeah, so obviously we can do a lot better than that trivial bound. So Tarjan actually invented this technique called multiple partitioning. So the big idea is that you basically group the edges and then you count each group. So each group is sort of categorized based on how big your rank jump RW minus RV is. So I think it will be a bit daunting to skip ahead to the full proof, because you sort of need to get acquainted with this technique. So I'll actually illustrate with some easy examples first. Yeah, and we do not, in these easy examples, we will not assume weighted union, only path compression. So we categorize edges into small or big edges. So you can draw an axis representing the rank, and then you can sort of draw how each edge along the axis. And I will also draw these vertical lines at every square root n. So these are sort of like checkpoints. So I'll say an edge is big if it passes at least one checkpoint. So if from RV you increase to RW, you will encounter some number of the form k times ceiling n, square root n. And an edge is small if it doesn't pass any checkpoint. And we also call an edge terminal if there are no other edges of that size happening after it in the partial find. So as an example, if in the first partial find I encounter a big edge, then a small edge, and a small edge, and so on, the terminal edges will be the last small and the last big. So I bolded them. And similarly for the second and third partial finds.
Sorry, so for big edges, is it roughly corresponding to things where the path compression compressed a lot?
Yes, roughly. But notice that it's possible that it's possible for the edge to technically be very small like this, but it still passes a checkpoint.
Oh.
So you still consider that as a big edge.
So it's not the absolute.
Yeah, it's not the absolute. It's more like whether you pass some important checkpoint or not.
Okay.
Yeah. So now we can actually group our edges into small terminals, big terminals, small non-terminals, and big non-terminals. So we can actually handle the first two first, because we observe that actually there are at most m small terminals, because it can only appear once per partial find. And similarly for the big terminal. So m plus n is 2m. So now we just have the rest to handle. So that means we need to actually count how many non-terminals are there. And now the important technique is to actually group the non-terminals by the source node. So for example, I've split it into different colors. So imagine the blue smalls are the ones starting from V, the green ones are starting from say V1, and the oranges are starting from V2. So we are further subgrouping. So this is what a generic partial find looks like. So we have V to W, say the rank difference is K. And by definition of it being non-terminal, we will also encounter some other edge further down the partial find, so V prime and W prime. So if we take this and this into account, and if W prime prime is the end of the partial find, then now V's new parent will be W prime prime, and the rank jump will increase by at least 1.
Is k plus 1 because there's another jump of at least k in the partial find.
Sorry?
There's another jump of at least 1. Why can't there be a jump?
Oh, because these two might be equal actually. W might be equal to V prime, and W prime might be equal to W prime prime. So if you like, in the worst case, it will actually just be like a sort of a single hop kind of thing. Yeah. So now we ask, how many times can we do this process of increasing by 1? So we can't do this forever, because after a certain amount of time, ceiling square root n times, you will actually pass a point where this rank jump will become so big that now we actually are forced to cross a checkpoint. So now from small it becomes promoted to big. So that actually gives, sorry? So actually that gives us an upper bound on the number of small non-terminals.
I'm sorry, E here is the total number of edges, is it?
Yes, along all the partial finds.
Along all the, so it's a sum
Yes.
over all the partial finds.
Yes.
Okay,
It's basically in your original setup, you know, in the finds that traversing the edges, right? It's basically summing up all the path lengths.
Oh.
Yeah.
Okay. But don't we double count? Let's say I have A, B, and C, then I sum up the partial find on B and sum up partial find on C, then it's like I double count.
Partial find on B and partial find on C. What do you mean?
Is E just the total number of edges?
Yeah, it's a total number of edges. There's no double counting. Yeah. Yeah, so we can upper bound the number of small terminals from a given node. And so if we consider all the nodes, it will become n ceiling square root n. So now we just have the big non-terminals to worry about. But the principle is quite similar. So if you have V to W a big non-terminal, and it ends all the way at say W prime prime, then this giant jump must actually skip past one more checkpoint, because our initial edge skipped past one checkpoint, and we encounter another edge where it skipped past one checkpoint. So in total, you skip past 2 checkpoints. So how many times can you repeat this process of skipping past an additional checkpoint? So it's bounded above by the total number of nodes in our tree in the first place, which is n. So n over ceiling square root n gives us an upper bound of square root n. So if we add up for all possible source nodes, we get the same bound. So yeah, so now we can bound E by O of m square root n. So this is better than our mn bound from just now. But this we can try something even more powerful to get a better bound. So instead of small and big, right? What if we had even more sort of tiers of edges? So I'll have tiers 1 to z plus 1. And now instead of just one kind of checkpoint, I'll have tiers of checkpoints. So tier 1 checkpoints will just be every number tier 2 checkpoints will be 02468, tier 3 will be 048, and so the higher tier the checkpoints, the more sparsely spaced out they are. So I will categorize an edge as being tier I if the highest tier checkpoint, so for example, if from C to D the highest tier checkpoint is tier 2, so this thing will be tier 2, and this thing will be tier 3, and because G to H passes this giant tier 4 checkpoint, it is tier 4. But there's also a special tier Z plus 1 checkpoint which basically sort of collects everything that we haven't captured so far in the first Z tiers, like all the leftovers. Yeah. So now if we use this tier system, we actually get this summation, and now we have to upper bound each part. So a similar argument as just now lets us upper bound the number of terminal edges very easily. So m, because there are Z plus 1 tiers and m partial phi, so m times Z plus 1. So now we have to bound the number of non-terminal nodes of a given tier. So we do the same thing of grouping them by the edges that come from V, the edges that come from V1, the edges that come from V2, and so on. So observe that actually every other tier, say tier I checkpoint, say 4, 6, 8, every second one is actually a higher tier checkpoint. So basically if you have an edge of say tier 2, and then you have an edge of another edge of tier 2 like this, and if you combine to form the new edge, it's guaranteed to pass a higher tier edge. So that means that there is at most one tier I non-terminal from a given node. So we can have an easy upper bound of nz. And the tier z plus 1 non-terminals, the leftovers. So now the upper bound must be based on the total number of nodes. So every tier z plus 1 non-terminal skips over a tier z checkpoint, and we can skip over them as long as the rank jump is bounded above by n. So we just divide n over 2 to the z, which gives us this thing. So now we actually have a concrete bound for E which holds for an arbitrary z. So now we can actually fix, say, z equals log n, then we sub that in, and now we get a bound in terms of m and n. So this is, I believe this is the optimal bound if we only assume path compression and no weighted union. So yeah, so now let's use multiple partitioning to its full power. So now we actually define the tiers of checkpoints based on the Ackermann function. So tier 1 will be every number as usual, tier 2 will be every even number, tier 3 will be based on the powers, tier 4 will be 2, 4, 16, then 2 to the 8 and so on. And we define an edge to be tier I, same as just now. And yeah, so familiar, right? We just have to go through the whole process of bounding each term. So this is also basically the same argument as just now, because every other tier I checkpoint, or every other tier 1 checkpoint is a tier 2 checkpoint, because these tier 2 checkpoints are like every other number, like all even numbers. Yeah. So now the hard part is handling tiers 2 to z non-terminals. So actually we have to do something a bit more subtle here. We actually have to not just group the edges by their source node, but we also have to consider the actual rank of this V. So suppose that given the rank of V, we can say J such that rank of V is between these two things. So J depends on the rank of V. Every tier I non-terminal of V causes it to skip over an extra tier I checkpoint. Okay, so we can skip over tier. Yeah, so we can skip over checkpoints as long as as long as we don't pass this, because this is a tier I this is supposed to be tier I checkpoints, and this is a tier I plus 1 checkpoint because I define we can skip over as many checkpoints as long as this is bounded above. And we use the recurrence of the Ackermann function to write it as this. So basically, every a minus 1j checkpoints is every tier a minus 1j checkpoint is a tier I plus 1 checkpoint. So this will give us our upper bound for the tier I non-terminals from V. So earlier I derived a very small upper bounds, like for example, it's upper bounded by n, right? But now it's like ai minus 1j is like it's a large number, right? It's a very large upper bound. So this is where we need to use weighted union. So essentially,
Sorry, where did the J originate from?
J depends on the rank of V. Basically, if for example I minus 1 is 4, right? And for example the rank of V is here, right? Then J will be either 1 or 2. Like it'll represent this number. Like which like
Oh, I see.
in between which
Index
2
of-
checkpoints you are in. Yeah, so with weighted union, we will actually see that there are very few vertices V where the J is very high. So that means large upper bounds occur very rarely. So averaging out everything actually turns out to be, you'll see it turns out to be a reasonable bound. So we need to use some facts about the weighted union. So let dV be the number of descendants, so including the children and all the grandchildren and so on. So theorem 1, if T is formed by weighted union, so if we bunch up all the unions and they follow the weighted union rule, and if V's parent is W, then W has at least twice as many descendants as V. So I chose to give a pictorial proof. So basically the only way that the number of descendants of a given vertex can change, right, is if you attach something to it, if you attach something new to it. For example, a new subtree. But then by the weighted union rule, you know that A is at least B. So now this total number of descendants of B becomes A plus B, which is more than twice of B. Yeah, and so B prime is one of the children with descendants B, and B is the parent with greater than 2B. So this property still holds. And an easy consequence is that we can lower bound the number of descendants by the rank. Yeah, and we have a global upper bound on the rank of any given vertex, which will be important. Yeah, so recall this expression from earlier where we tried to group the vertices V based on their rank, right? So this is now we're actually sort of counting how large this sort of group by rank is. So yeah, so I tried to write out an explanation, but I realized the paper is already quite concise. So basically, if consider all the rank k vertices for some k, and each of them will have some large number of descendants, but the total number of descendants must still be less than the total number of nodes. So the number of vertices of rank k is bounded above by n over 2 to the k, and if you sum up the ranks from aij to aij plus 1, you get this expression. So note that as j increases, this thing sharply decreases. So you'll see that this actually counteracts our massive growth of the upper bound just now as j grows. Yeah, so we can revisit the proof. So divide the elements V based on their ranks. There are that many of them within this rank group, each with that upper bound. So if we just multiply them and we do some manipulations, we actually get ON, which is amazing. So now if we sum over all V, we get O of NZ. Yeah.
So what is N and L?
What is N and L? Oh, these are all edges of tier I, and these are the terminal edges of tier I. So this is like some notation. So the paper used this like symbolic notation, but I feel like writing out as non-terminals, terminals makes it a bit easier to understand. Yeah, so we handle all the tier 2 to Z. Now we handle the leftovers. So it's basically the same argument. we use the global bound for the rank here. So we can skip over as many tier Z checkpoints as we want, but the difference in rank cannot be greater than the maximum rank, which is bounded by log n. So if we define this other inverse Ackermann function, minimum I such that this is greater than log n, there are at most that many of them. So this basically represents at the z minus 1 level of operation, how many times can I apply I before, sorry, how many times can I apply that z minus 1 operation before the Ackermann thing grows bigger than log n. So if we sum over all v as usual, we get this upper bound. Yeah, and so we've handled all the terms. So now we just have to plug in a specific value of z, and there's a bunch of manipulations you have to do, but it all reduces down to m times Ackermann m in the end. So hooray, that is the proof. So yeah, additional remarks. This, I only proved the upper bound, but actually in the same paper, Tarjan goes on to prove a lower bound. So to do that, he actually constructed he sort of constructed a sequence of counterexamples to show that the lower bound of the time is not linear. So for each number k, we can construct some tree and can find some sequence of partial finds that on average take more than length k. So it cannot be, it's bounded below by every constant, so it cannot be constant. Yeah, thank you. Any questions? You can give your talk.
No questions, then we'll take a few minutes break before we start. Before we go with coding.